Alright, 3.2 is on polynomial functions and their graphs. Here are our objectives. So let's start with the definition of a polynomial function. So n is a non-negative integer, and a sub n all the way down to a naught represent real numbers, where a sub n is not equal to 0. The function defined by f of x equal to this expression is called a polynomial function of degree n. The number a sub n, the coefficient of the variable to the highest power, is called the leading coefficient. So a sub n is our leading coefficient. And n in this power represents the degree of the polynomial. Alright, so polynomial functions of degree 2 or higher have graphs that are smooth and continuous. By smooth, we mean that the graph contains only round curves with no sharp corners. By continuous, we mean that the graphs have no breaks and can be drawn without lifting your finger from the rectangular coordinate system. Alright, let's go in our books to page 360. We're going to look at the following problems. Let us start with number 3. And it says, determine which functions are polynomial functions. For those that are, identify the degree. So number 3 has g of x equal to 7x to the 5th power minus pi x to the 3rd power plus 1/5 x. And the question is this expression a polynomial function? Well, in order to be a polynomial function, you're going to need the powers to all be positive integers. So 5 is positive integers, so we'll say whole numbers. 3, and the number on x is a 1. So that checks out. And then our coefficients can be anything. So this right here is a polynomial function. It's in the correct form of the expression on the previous slide. And our powers are all positive whole numbers. All whole numbers. Alright, let's look at number 7. It has f of x equal to x to the 1/2 power minus 3x squared plus 5. And again, it says, is this a polynomial function? Oh, and by the way, the degree in number 5 and number 3 is 5, is the highest exponent or power. All right, number 7. This is not a polynomial function because the power on the first x term is a half. Your powers have to be whole numbers. So whole numbers are 0, 1, 2, 3, all the way up. This is a half, so therefore it's not a polynomial function. All right, number 9. F of x equals x squared plus 7 all divided by x to the 3rd power. Well, we notice here that we are dividing by x to the 3rd power. On the previous slide, the expression for a polynomial function didn't have any variables dividing. So you cannot divide by x to any power. So this is not a polynomial function. All right, let's move on down to number 12. And it says, identify which graphs are not those of polynomial functions. So number 12 has a graph, that looks like the following. And it says identify whether or not this is a polynomial function or if it isn't a polynomial function. So, polynomial functions are smooth and continuous. However, if I travel on this graph, I'm going to hit a corner, which is a sharp corner. Therefore, this is not smooth. This is not a polynomial function, and that's because it's not smooth. In order to be smooth, it should not have any corners. All right, number 14. So now we're looking at a graph that looks like the following. We must determine whether or not this is a polynomial function. Well, we notice that it is smooth. You see it has round curves, there's no corners, and it is continuous. If I was to take my pencil and trace this, I never pick my pencil up as I'm tracing the graph. So it is smooth and continuous, so it is a polynomial function. All right, now let's move forward. The end behavior of polynomial functions. The end behavior of a graph of a function to the far left or to the far right is called the end behavior. So basically, you're looking at how the graph tails off to the left and tails off to the right. Although the graph of the polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves to the far left or the far right. The sign of the leading coefficient a sub n and the degree of n of a polynomial function reveals its end behavior. So, in order to tell the end behavior of a polynomial function, you need two pieces. The first piece is the leading coefficient a sub n, and the second is the degree, which is n. Alright, well, as x increases or decreases without bound, the graph of the polynomial function eventually rises or falls. In particular, the sign of the leading coefficient and the degree of n of the polynomial function reveals its behavior, what it just told us. So the leading coefficient test uses the leading coefficient and the degree of the polynomial to determine its end behavior. Alright, so this is how it breaks it down. We're going to start off looking at n as odd. So n is odd, which means your degree is odd. So you have odd degree, and if your leading coefficient is positive, then the graph falls to the left and rises to the right. So as you're reading your graph, remember we read from left to right. So from left to right, this is falling to the left and rising to the right. So if your n is odd, meaning your degree is odd, and your leading coefficient is positive, it falls to the left, rises to the right. If your leading coefficient is negative, then it rises to the left and falls to the right. All right, let's look at when n is even. So now your degree is even, and your leading coefficient is positive. So your graph would rise to the left as well as rise to the right. And if your leading coefficient was negative, then your graph would fall to the left as well as fall to the right. All right, let's go in our books to page 360. We're going to look at the following problems. Let's start with number 15. It says use the leading coefficient test to determine the end behavior of the graph of the given polynomial function. Then use this end behavior to match the polynomial function with its graph. So number 15 has f of x equal to negative x to the fourth power plus x squared. Well, to first determine the end behavior, we need the leading coefficient and the degree of the polynomial. So the leading coefficient is a negative 1, and the degree of this polynomial is 4. So our degree is even, and our leading coefficient is negative. Well, the previous slide told us that when we have an even degree, and our leading coefficient is negative, then our graph would fall to the left as well as fall to the right. So this graph falls to the left as well as falls to the right. Therefore, knowing this information, now let's look in our books at the graphs labeled A through D and determine which one falls to the left as well as falls to the right. And in that case, it would be B. Falls to the left and falls to the right. All right, let's look at number 17. So this time we have f of x equal to x minus 3 whole thing squared. And again, we need to determine the end behavior. Now, before we do this, we need to multiply this out. Our polynomial function is written as a combination of different terms by adding and subtracting. So this x minus 3 whole thing squared should be multiplied out to x minus 3 times x minus 3, which is x squared minus 6x plus 9. Okay, so now we can determine the leading coefficient, which we get to be a positive 1, and we can determine the degree of the polynomial, which we get to be 2. So now we have an even degree with a positive leading coefficient. So as I said on the previous slide, this rises to the left and rises to the right. So let's find a graph that rises to the left as well as rises to the right. And it would be letter A. All right, let's move over to number 19. Now it says use the leading coefficient test to determine the end behavior of the graph of a polynomial function. So f of x is equal to 5x to the third power plus 7x squared minus x plus 9. And we must determine the end behavior. So to do that, we need the leading coefficient, which is 5, and the degree of the polynomial, which is 3. Now we have odd degree, and our leading coefficient is positive. Well, with odd degree and a positive leading coefficient, we are going to fall to the left and rise to the right. Fall to the left and rise to the right. All right, number 21. So we have f of x equal to 5x to the fourth power plus 7x squared minus x plus 9. So again, to determine the end behavior, we need the leading coefficient. And we need the degree. Alright, well the leading coefficient is 5, and the degree is 4. So we have even degree with a positive leading coefficient. Well, that tells us that we're going to rise to the left as well as rise to the right. Good. All right, now let's talk about the zeros of polynomial functions. If f is a polynomial function, then the value of x for which f of x is equal to 0 are called the zeros. These values are also called roots or solutions of the polynomial function when f of x equals 0. Each real root of the polynomial function appears as an x-intercept of the graph of the polynomial function. So this is telling us that the word x-intercept, roots, solutions, and zeros all mean the same thing. You set f of x equal to 0, and you solve for x. If r is a 0 of even multiplicity, so it means it appears an even number of times, so that can be 2, 4, 6, 8, etc., then the graph touches the x-axis and turns around at r. So it touches the x-axis and turns around at r. That's if we have even multiplicity. If r is a 0 of odd multiplicity, then the graph crosses the x-axis at r. Regardless of whether the multiplicity of a 0 is even or odd, the graph tends to flatten out near zeros with multiplicity greater than 1. So if it's odd multiplicity, it crosses the x-axis at r. And if it is even, then it touches the x-axis and turns around at r. All right, let's go in our books to page 360. Let's start by looking at number 27. So it's really page 361. All right, number 27. It says find the zeros for each polynomial function and give the multiplicity for each zero. State whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. So 27 says f of x is equal to 4 times parentheses x minus 3 times x plus 6 raised to the third power. And we must find the zeros. So the first thing we want to do is set f of x equal to 0. So we have 4 So we'll have 4 times x minus 3 times x plus 6 raised to the third power equal to 0. And then step 2 would be to solve for x. Alright, so let's solve for x. Well, 4 is out here by himself. He's just a constant. He's multiplying all of these parentheses. So I'm going to divide by 4. And now we're left with x minus 3 times x plus 6 raised to the third power equals 0. And then we need to solve for x still. So remember, the rule was when you have two things multiplied together and they equal 0, then you set both things equal to 0. Well, here we're saying x minus 3 times x plus 6 to the third power equals 0. So we have x minus 3 equals 0, and x plus 6 raised to the third power equals 0. So this is just x equals 3, and it only appears one time, so it has multiplicity 1. Here it says x plus 6 raised to the third power equals 0. Well, to get rid of the third power, we would actually take the cube root on both sides. Cube root in the third power disappears, so I have x plus 6 equals 0. So x equals negative 6, but it has a multiplicity of 3 because it actually appears 3 times. So we found our zeros and our multiplicity. So then the last thing we need to do is determine, well, does it cross the x-axis or does it touch and turn around? Well, at x equals 3, because I have odd multiplicity, it is going to cross the x-axis at x equals 3. And this one, x equals negative 6, has a multiplicity of 3, which is also odd. So again, we're going to cross the x-axis at x equals negative 6. Okay, problem 31, I will leave for you to do. It's odd, so you can find the answer in the back of the book. You can email me if you have questions working on this one. All right, let's continue. The intermediate value theorem. Let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c equals 0. Equivalently, the equation f of x equals 0 has at least one real root between a and b. So what they're saying is, if I have a graph, so let's see if I can make up a graph. Let's see if we can do this. Okay, so let us for now pretend like A is here, and let's put B right here. Okay, so if I have a graph, and if they say f of A and f of B have opposite signs, so if this is A, f of B must be right, f of A must be right here, and if this is B, then f of B must be down here. So you notice f of A is positive and f of B is negative. So if f of A and f of B have opposite signs, this one's positive and this one's negative, then they're saying then there is at least one value of C between A and B. A and B are found on the x-axis. So here's A and B, and they're saying there's at least one value of C between A and B for which f of c is 0. And that position must be right there, because f of c equals 0 means you are on the x-axis. So basically all they're saying is, if f of a and f of b have opposite signs, then there is at least one 0 found in between a and b. Or the graph crosses the x-axis at C. That is the intermediate value theorem. All right, let's go in our books to page 361. Let's look at number 33. It says, use the intermediate value theorem to show that each polynomial has a real 0 between the given integers. So f of x is equal to x to the third power minus x minus 1, and we're looking between one and 2. Okay, so all we need to do is show that we have a real 0. So the first thing we're going to do is we're going to find f of 1. Okay, so find f of 1. So let's go ahead and do that. That's 1 to the third power minus 1 minus 1, which should be negative 1. And then you want to find f of 2. So that's 2 to the third power minus 2 minus 1, which is 5. Okay, so now we see that f of 1, that's negative, and f of 2, well, that's positive. So since they are opposite signs, there must exist a c in between 1 and 2 such that f of c equals 0. So this is your proof enough, because f of 1 and f of 2 are opposite signs, there exists a real 0 between 1 and 2. Alright, the turning points of a polynomial function. In general, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. At most n minus 1 turning points. And then here's a strategy for graphing a polynomial function. The first thing you want to do is use the leading coefficient test to determine the graph's end behavior. The second thing would be to find your x-intercepts and determine if, their multiplicity, if it's even or if it's odd. Then you can find the y-intercepts, look for symmetry, as well as turning points. Alright, let's go in our books to page 361. We're going to start by looking at number 49. 49 has f of x equal negative 2x to the fourth power plus 4x to the third power. And there are a total of 5 parts here. Part A says use the leading coefficient test to determine the graph's end behavior. So, first thing we see that our leading coefficient is equal to negative 2, and the degree is equal to 4. So we have a degree of 4 and a leading coefficient of negative 2. So your degree is even, and your leading coefficient is negative. So your graph falls to the left as well as falls to the right. So it falls to the left as well as falls to the right. And then part B says find the x-intercepts and state whether the graph crosses the x-axis or touches the x-axis and turns around. So to do that, we're going to set f of x equal to 0. So we have negative 2x to the fourth plus 4x to the third equals 0. I'm going to factor out a negative 2x to the third, and I'll be left with x minus 2 equal to 0. And then you set each thing equal to 0, so negative 2x to the third equals 0, as well as x minus 2 equals 0. I'll end up with x equals 0 here. And notice that it has multiplicity of 3. And then this one says x equals 2, and it has multiplicity of just 1. So both of these cross the x-axis at their respective zeros. Alright, part C says find the y-intercept. To find the y-intercept, you just set x equal to 0. So let's see, f of 0 is going to be negative 2 times 0 to the 4th power plus 4 times 0 to the 3rd power, which is just 0. So the y-intercept is just 0. Part D, determine whether the graph has y-axis symmetry, origin symmetry, or neither. Now this is not something we covered in the slide, so let's talk about it. The first thing you want to do is go ahead and find f of negative x. Notice that it always says f of x. So when we deal with symmetry, go ahead and find f of negative x too. So that's negative 2 times negative x to the 4th plus 4 times negative x to the 3rd. Everywhere you see an x, now you're making a negative x. So negative x to the 4th, well, because that's the 4th power and it's even, this negative means nothing. So this is still negative 2x to the 4th power. But because this is odd and there's a negative on the inside, that actually comes out. So we have minus x to the 3rd power. 1 second. Okay, so now if f of x equaled f of negative x, then you would have y-axis symmetry. Okay? It's just their way of saying that it is actually an even function. If f of x would have been equal to the negative f of negative x, then you would have had origin symmetry. Which means it's really just an odd function. And then, of course, if neither one of these works, then you have neither. So, f of x was equal to negative 2x to the 4th plus 4x to the 3rd. When we look at f of negative x, it's not the same because this minus sign should have been a plus sign. So the first one fails, so that's gone. They're not equal. And then when we look at the second one, they have to be opposite signs, right? This has to be a positive, and this one has to be a negative. Well, the negative works, but he is still negative. He didn't become positive. So this one's out. So the answer here is neither. And then part E wants you to graph. I'm going to let you graph this with your graphing calculators to verify that you get all of these characteristics that we have. So part E we'll write as graphing calculator.